Newton's second law of motion is probably best understood in equation form. And here you see it in the box, F net equals m times a, where F net is the net force on an object measured in newtons. And we're going to use capital N for newtons. That's the symbol for the units. Little m stands for mass in this context. The units for mass will be best measured in standard units, which are kilograms. And we'll just use kg for that. And then the A stands for acceleration, measured in meters per second squared. I'll just abbreviate that, meters per second squared. I mean, you could have miles per hour squared, but the standard is meters per second squared. So here's the ball from yesterday's notes, the free body diagram with some abbreviations and extra information. The force of gravity, we call it F sub g, g for gravity, is 5 newtons straight down. The force of air resistance is 2 newtons straight up. And I'm giving you the mass of the ball here to be 0.5 kilograms. We will now apply Newton's second law of motion, which is F net equals ma. F net here is the vector sum of the two vectors. And when they're in opposite directions, you subtract. You take the bigger one minus the smaller one. We have 5 newtons down, 2 newtons up, which we could have done in our head, but I'll write it out. 5 minus 2 is the expression for the net force equals the mass, 0.5 times A. All those units are appropriate and standard, so we can go ahead. It's going to be 3 equals 0.5A, so A equals 6 meters per second squared down. Because the net force, the bigger force, is downward. That's our acceleration here in this particular situation. Alright, let's take another look. Here's the same ball once again, and I'm abbreviating a lot more now. The 5 newtons is the force of gravity, which is the weight of the ball, pulling straight down. The force of air resistance is 4 newtons, because when you're traveling upward, the force of air resistance is against your motion. And the ball has a mass of 500 grams. That's the same ball. The little g there means grams, but converted into kilograms, it's 0.5 kilograms, the same as on the left side here. So we're going to apply F net equals ma. Making sure we convert everything into the proper units. So the F net here will be 5 plus 4 instead of 5 minus 4, because you notice both vectors are in the same direction. I'll write that out. Okay, equals the mass in kilograms, 0.5 times A. Once again, we're trying to find A. So we're going to have 9 equals 0.5A, or in other words, A will equal 18 meters per second squared. Once again, downward. Even though the ball is traveling upward, the acceleration is down. The ball is slowing down in the upward direction. Another clue here is that the acceleration is always in the direction of the net force. The net force is down. There's a lot of force slowing down this ball. 18 meters per second squared. Notice that in both these cases here, the acceleration is not 9.8 meters per second squared. That will always occur and only occur if there's no air resistance. No matter what the mass of any object is, the acceleration will be 9.8 or 10 meters per second squared when there is no air resistance. Same ball now. Mass 500 grams, 0.5 kilograms. Weight of 5 newtons straight down. But now we do not know the force of air resistance. We're going to find that using Newton's second law. I've just labeled it F. In blue is no magic color here, but if you want to use subscripts, you may, like F sub air. But applying Newton's second law, F net equals ma. Always write down the general form and now plug in. And the rule is this: when you don't know the forces, and we're going to be dealing mostly with 2 forces, but you can have problems with 3 or 4 or 5 forces. We'll stick with 2 forces for now, or even sometimes just 1 force acting. When one force is acting, that is the net force, but here we have to combine or subtract or add. In this case, we subtract because the two forces are in the opposite direction. Take the big force minus the smaller one, and we know it's accelerating down, therefore the bigger force is in the downward direction. The 5 newtons is bigger than the force of air resistance, so it will be 5 minus F equals 0.5 kilograms times 4. Once again, the F here I have now is not F net, it's the actual force of air resistance. If we do the math here, 5 minus F equals 2. Therefore, F equals 3 newtons, as directed in the diagram upward. Here's another scenario. We have a different ball, and you can tell, first of all, it looks different. It's got dots instead of stripes. Maybe it's a golf ball. And it's lighter. It weighs 3 newtons. That's the red vector down, the force of gravity. And the force of air resistance here is 6 newtons straight down in this case, because the ball is going up. The force of air resistance can be here greater than, less than, or equal to. So here's the first case we've had where the air resistance is bigger than the actual weight. That's a possibility. And we know the acceleration is 30 meters per second squared straight down. So applying Newton's second law of motion, that is F net equals ma. So F net, once again, you look at all the forces, and once again we're dealing with 2 here, and you got to either add or subtract. In this case you'll add because they're both pointing downward. And I made the numbers simple enough, but I'll write it out. 6 plus 3 equals m, unknown for mass, times a, watch the units, they're all good here, so we can just plug in the numbers as given, 30 meters per second squared. So you're going to have 9 equals m times 30. Do the math here, get m equals 0.30 kilograms. That's the mass of the ball. 0.30 kilograms. It would be 300 grams if you convert it to grams. Once again, here's a diagram from yesterday. A person in an elevator, but they're accelerating upward. There are 2 forces acting on the person. The force of gravity, F sub g, the weight of the person, 550 newtons straight down, and the force of the floor pushing up on them. If you want to call it the force of the elevator, but it's whatever you're standing on, whatever's touching you, the floor in this case, upward at 800 newtons. And the only way to get you to accelerate upward is for the floor force to be bigger than the gravitational force. And by the way, the blue force here, the force of the floor, is what you feel like you weigh. You're going to feel like you're a little bit heavy when you start up. You feel like you sink into the floor a little bit. Your weight never changes, but you kind of feel heavy when the elevator starts up. The feeling you have is the 800 Newton force. But once again, we're going to apply Newton's second law, which is F net equals ma. So we're trying to find the acceleration of this person. F net is big force minus small force if they're opposing, which they are. One's up, one's down. So it will be 800 minus 550 equals your mass, 55 kilograms, already in kilograms, times A. So we will have 250 equals 55A. Divide both sides by 55, you get your acceleration upward of 4.5 meters per second squared. That's a pretty healthy acceleration. Most elevators don't have an acceleration quite that good, but that's the acceleration in this case, provided by the large floor force. Well, the net force, the excess force above the 550. Most of the time when you're in an elevator, you're moving at constant velocity. Only when it really starts up or stops are you accelerating. Accelerating down, like for example, if you're at the top floor and you want to go to the bottom floor, the elevator momentarily accelerates downward. But for most of the trip, the floor force will be equal to your weight. Only while you're accelerating will the floor force be different and feel different than your actual weight. For example, here now in this case, you need to accelerate going down to get up to a speed, and you will maintain a speed. But you need to accelerate first to get up to a certain speed. Applying Newton's third law, F net equals ma. We're going to try to find the floor force. And by the way, the floor force is the force that you feel like you weigh. You feel a little bit light when the elevator first starts up. Starts dropping from a top floor to a bottom floor. If the floor totally gave way and disappeared, you would fall with an acceleration of 9.8 meters per second squared, free fall, straight down. Obviously, we don't want that in an elevator. But once again, F net equals ma. Take the big force minus the small force. The floor force has to be the smaller force because you are accelerating down, or in other words, the bigger force has to be down to cause the downward acceleration. So we have 550. Once again, it's the net force that causes the acceleration, minus the force of the floor, I'm just going to call it F, force of floor, equals your mass, 55, times 3. So we have 550 minus F equals 165. And if you move things around, move the F over and subtract the 165, you get F, the floor force, equals 385 newtons, at least during this acceleration phase. Once the elevator is done accelerating, what happens is the internal mechanism of the elevator causes the floor force to go back to 550. So when the floor force is 550, you will be moving with constant velocity. You will not accelerate. And once again, that happens for most of your ride. The only time you accelerate is on startup, and on stopping, you'll feel some weird floor forces.